Hey everybody, great to see you again. Mr. Smith here. In our first slide deck, we looked at heat engines, and they're complicated. They have pressure, volume, temperature going on, internal energy of the gas, heat flow, work, all those things being done. And the first thing I wanted to do was to own up to the fact that, yeah, in real life they're complicated, but they're understandable. And what's really interesting to me is if you look at this chart full of different types of heat engines, you have on the top external heat engines like your freight train engine, and you have internal combustion engines like your diesel and the gasoline engine that we use and the one that they use in jet airplanes. All of these use the same basic vocabulary words that we learned in the first slide deck. You have isobaric transitions where pressure is held constant. You have isovolumetric, also known as isochoric transitions. You have isothermal transitions where temperature is held constant. And what we didn't talk about was one of the most common ones. It's adiabatic. It's a little complicated, but in real life, it's actually very understandable. And that's going to be the first thing we talk about right now. So adiabatic just means that the transition is so sudden that no heat can be transferred in and out. So in a way, it's the opposite of isothermic. We did the squeezing of the gas in our Boyle's Law experiment so slowly that the temperature of the gas could stay constant because heat could flow out of the cylinder as we compressed it. Okay, so what's really neat is that adiabatic not only exists in engines, as we'll see, it exists in the weather of our planet in a really important way. If you live in Calgary, you'll know all about these things. There's a feature called the Chinook Wind that can happen in winter, and when it happens, it can take away a foot of snow in a few hours. And so here's how it works. If you have cold air approaching from, let's say, the Arctic, that cold, wet air can vault up to the top of the mountain range, okay? So it's just forced down by northern winds. But what can happen as the cold air, because it's dense, begins to descend is that the atmosphere squeezes it. The atmosphere does work on that cold air and squeezes the gas molecules together. So there's work being done, and because the transition is so rapid, the heat energy is not allowed to bleed out of that air. It doesn't escape. So what happens is that work turns into U, the internal energy of the gas, and the temperature skyrockets. So you can get this thing that's called the Chinook breeze. It's a really warm burst of air that can happen in the middle of the winter. And like I said, it can be high-speed winds that can be really warm. And it's just an example in the real world of how adiabatic happens. So a really cool example that's very practical too of adiabatic happens in jet engines. So there's basically 4 stages to this process. The way a jet engine works is it takes in air, just ordinary breathing air, atmospheric pressure, or even lower when the planes are at altitude, and it squeezes that air through a series of smaller and smaller stages with a compressor. So that's this transition from 1 to 2. What I want you to do is to practice the thought process that we started in the first slide deck. I have some gas. We do work on that gas. And because the Q is not allowed to escape in this adiabatic transition, the temperature of the gas skyrockets. So that's useful in the burning of the fuel. So what happens in the first stage of a jet engine is we do an adiabatic compression. So the air is squeezed very suddenly, warming up the gas. Okay? The next thing that happens is we dump some thermal energy in, and that happens right here in the combustion chamber. So that's done at constant pressure, and if you think about it, for the Q to go in and the pressure not to go up, this gas is already starting to do work for us as it flows out the back towards the propeller, okay, towards the nozzle. Now, in the nozzle, we get this transition right here from 3 to 4. It's so sudden that, again, in this idealized transition, it's perfectly adiabatic. No heat escapes or goes anywhere. And the gas does a lot of work for us. So in this combustion stage right here and in this expansion stage in the nozzle, a ton of area is being carved out where this jet engine does work for us. And then finally, in the nozzle, we have the atmosphere starting to condense this gas back down to a smaller volume at atmospheric pressure. And as the gas is exhausted. Okay, so anyway, adiabatic transition is really important in the real world, particularly in jets. What I want to do is really dive in and give you the most technical example of a jet engine, no, not a jet engine, the actual made up one that we started to talk about in our first slide deck. And let's tackle that right here. So the first thing we're going to do is to give you a few numbers. So this is 100 kilopascals, this is 500 kilopascals, we had 1 cubic meter, and we have 5 cubic meters out here. Okay? And we started in our first engine looking at the transition from A to B, which we said was isobaric. So this transition happens at constant pressure, and what we said was that when we squeeze on the gas, it's the same thing that we did in our cylinder with our Boyle's Law gas. We're squeezing on the gas, except what's different is that this is happening so that the pressure stays constant. And the only way that can happen is if heat is pulled out of the gas as we do work. And the final thing we said was that the work that's done in this gas is the area under the curve. Okay, so I wanted to focus on that part right now. So P delta V is the work that's done in one of these transitions. And it's not tricky to do. The pressure is easy to figure out. It's constant, 100 kilopascals. So you'll remember that that's 100,000 newtons per square meter. And I really like those kilopascals when I'm doing physics because they relate to newtons and meters. And what we see here is the change in volume goes from 5 to 1 is minus 4 meters cubed. And so the work that's done, or the P delta V, is negative 400,000 or 400 kilojoules. Okay, so that's work that's done on the gas, and it comes out negative, like I said it would. Okay, so that's your first type of transition worked out. It's the isobaric one. Now, isovolumetric, we know for a fact that because there's no change in volume, the work that's done in an isovolumetric step is going to be equal to 0. So what happens is, if they tell us that there's an increase, there's Q given to this gas, we know for a fact that that's going to be reflected directly as an increase in the internal energy of the gas. Okay, so that's what will happen in isovolumetric steps. Now finally, this last one's a little bit more sophisticated. We said that the area under this entire curve from C to A was going to be where the gas was doing work for us. But if you think about it, we've got a little bit of an issue here. It's not possible to do a simple version of P delta V because the pressure isn't constant. Now, in higher level thermodynamics, you're going to use calculus and you're going to integrate the area under this curve to get P delta V. What we can do, though, in our class, without having to reach for the idea of integrating over the function of pressure, is we're going to use the idea of average pressure. So if we can get the average pressure and multiply that by the change in V, then this is going to enable us to understand what's going on in this step. And it's actually a pretty good approximation. So the average pressure is going to be halfway between 500 and 100 kilopascals. So if I add them up and divide by 2, I get that the average pressure is 300 kPas. The change in volume as the gas expands is going to go from 5 meters cubed to back to 1 meter cubed. So we have a positive 4 meter cubed transition right here. And what I get out of that is 1,200 kilojoules of work being done here. So this is where I want to put all parts of our engine discussion together. So I get work done by the gas at a higher temperature than the time that I did the work on the gas. So what I'm going to do is come back with my red pencil here and just color in the work that we did on the gas in the first stage. So you remember that was minus 400 kilojoules from our first slide? Well, the way it all works is that the net area is the area that's bounded by the curve, and so it's really all of this in here. And so the area that's on the internal part of this graph is really the net profit or the net work. So the net work is going to be equal to 800,000 joules in this particular stage. Okay, so that's basically all the basics about how an engine is going to be giving us work, even if we do work on it. One final thing that I wanted to point out, I had said in the earlier slide deck that you could study a graph and understand if you were looking at a Boyle's law situation. So just notice that 1 meter cubed, so this volume times this pressure, is the same as 5 meters cubed, this volume times this pressure. So when P1 V1 equals P2 V2, you know that you're dealing with an isothermal and that the internal energy of the gas won't change. Okay, we're going to put all that stuff together, and you should be getting a little more comfortable with the idea of talking about Q and U and work together all at once. Okay, so that's a good segue to the work that we're going to do in class. I'll see you there. Take care and have a great day. Bring questions if you got them. See ya. Bye-bye.